Hello everyone, and welcome to Intel Architectural Access, Season 4, Intelligent Connectivity. I'm Carlos Cordeiro, an Intel Fellow and the Wireless CTO in Intel's Client Computing Group. I lead Intel's global wireless connectivity standards and ecosystem team, defining the next generation wireless technology innovations. I'm also the editor-in-chief of the IEEE Communication Standards magazine and an IEEE Fellow. In this episode, I'll be taking you through all things intelligent connectivity. Let's start by first unpacking what we mean by intelligent connectivity. Simply put, connectivity is what enables our devices to share, send, and receive data, and is the foundation for human-to-device and device-to-device communication. To send and receive data, we need a few things. We need an interface. In the case of wired interfaces, an additional physical connector and a cable that enables the connection. And we need a protocol. It is the language that is used to ensure interoperability across devices when exchanging data. Historically, these were separate connections, with peripherals being connected through USB, your internet through a LAN or RJ45, and your screen through VGA4 display cable, and the list goes on. Today, these different data types are communicated through discrete protocols and interfaces that run across a single cable, such as USB Type-C or Thunderbolt, or wireless connectivity such as Wi-Fi or Bluetooth. While many interfaces have merged into one, for example Thunderbolt, which can carry data, video, and power, many of the protocols have stayed the same or simply evolved along the way. By smartly leveraging and linking these discrete technologies, intelligent connectivity helps to drive innovation and efficiency across numerous experiences. Connectivity is the first point of entry of data to a device and the last port of call. As such, it sits at a sweet spot for the application of AI when it comes to understanding data usage and the surroundings of a device. As the number of AI-driven experiences continue to grow on the AI PC, so does the need for connectivity. AI experiences such as generative fill in Photoshop, stable diffusion, and chatbots all rely on large amounts of data. As each new application is added, the need for higher raw bandwidth, predictable latency, and reliable connection only grows, in turn leading to a substantial increase in network traffic and data consumption. Beyond the fact that AI experiences are increasing connectivity and bandwidth requirements, it is also being leveraged for intelligent connectivity experiences. When we talk about intelligent connectivity, we mean the combination of advanced technologies to create highly responsive, personalized, and efficient user experiences. Intelligent connectivity enables seamless communication between devices, allowing them to understand their surroundings and improve data processing and real-time decision-making. For example, intelligent connectivity can dynamically manage a user's environment by automatically setting lighting and room conditions based on the user's identity or time of day or calendar. We can also leverage connectivity technology to sense and provide secure access control when someone known or unknown approaches a device. Intelligent connectivity can significantly improve device pairing and extensions, like wireless display extension to the closest monitors while detecting which monitor is to the right or to the left of the central device. Or it can enable a Teams call transfer between your PC and your phone automatically when devices move closer or farther away, while maintaining continuity across both devices, allowing users to seamlessly switch from one to another without interruption. Additionally, AI can optimize network functionality by analyzing performance and adjusting parameters in real time to maintain optimal speed and reliability and reduce congestions to enhance the user experience. Or it can be used to dynamically roam between wireless and wired interfaces depending on the best connectivity available for a given traffic profile. Let's unpack some fundamental technologies that are empowering these intelligent connectivity experiences. Key to providing this contextual experience is the ability of a device to understand the context of its user. Wireless technologies play a fundamental role in capturing this context. For example, It allows us to sense movement and capture distances and directionality between devices. Let's start with wireless sensing. Wireless sensing uses wireless signals to monitor environmental changes for the purpose of things like detecting motion, interpreting gestures, and monitoring vital signs like breathing rates. There are three wireless sensing methodologies. First, and simplest, is monostatic sensing, where a single device is used. This could be, for example, a laptop sitting on your desk, and you want it to wake up when you approach it or sleep when you leave. Second is bistatic sensing. This is where two devices are used to perform a sensing action, with one transmitting a signal and the other one performing the sensing measurement, before possibly sending that result back to the first device. This could be used when, for example, you want your device to be locked and the alarm system turned on as soon as you leave your house. The third type is multistatic sensing. Multistatic sensing uses multiple devices to create a holistic contextual image of the world around them. This could include devices such as temperature sensors, security cameras, smart home devices, and many more. To bring Wi-Fi sensing to life, let's explore how monostatic sensing works in more detail. In essence, monostatic Wi-Fi sensing is very similar to the echolocation used by whales to hunt, where they send out sound waves and use the reflected waves to construct an image of their surroundings. In place of a whale, we have our device, such as a laptop. Like a whale, it sends out a signal and registers the echo to create a picture of its surrounding environment. In a particular implementation of Wi-Fi sensing, we need at least two antennas, which most modern laptops have. The reason we need two is that we need one to send the signal and the other to receive it. To detect nearby movement, we typically cannot receive the signal on the same antenna as the one we are sending it from. To perform Wi-Fi sensing, we need to understand what happened to the signals as they travel through the space. That information is called Channel State Information, CSI, in the world of Wi-Fi. But how do we get this information? It starts by using the preamble of a Wi-Fi transmission, which contains a known field called the long trailing field. Coming back to our laptop, the first antenna sends out a packet that includes the LTF. This known LTF pattern helps the receiver, in this case the second antenna, understand how the signal is being affected by the surrounding environment as it bounces off things like walls, furniture, and other interferences. The second antenna receives the LTF to estimate the condition of the wireless channel. This involves figuring out how much the signal has changed as it traveled through the air, allowing the receiver to adjust its setting to compensate for any distortions. The CSI is estimated from the LTF in frequency domain, using an equation that enables us to extract the CSI based on the receiver LTF field and how the wireless channel propagation changed this field because of effects such as multipath fading or shadow fading. The CSI estimation is then smoothed to deal with any hardware imperfections and other noise. This is done using a weighted moving average formula. The output of this process is the clean CSI, which can then be used as an input for an AI model. By employing machine learning models to analyze the CSI data, we can distinguish between different motion types, gestures, and environmental changes. By integrating advanced signal processing techniques and AI models over Wi-Fi networks, we are better able to deliver accurate and reliable results and transform them into powerful sensing systems, which we can use to do things like turn up the volume or dim the lights. We should also note that to ensure user security, Wi-Fi sensing only takes place on the device itself, without ever leaving the network. Beyond motion sensing, intelligent connectivity can also be used to wirelessly sense the proximity of devices, and even their directionality. For example, when you want to transition your Teams call from your laptop to your phone, we need to understand when to switch from one device to the other. Knowing how to proactively monitor the distance between devices is key to achieving this. To calculate the distance between two devices using Wi-Fi, we use the time of flight principle. Time of flight can be likened to throwing a baseball to a friend. We know when the ball was thrown, when your friend caught it, how long it took your friend to throw it back to you, and when you caught it. To calculate the distance, we need the speed of the baseball multiplied by the average duration of the single throw. In the case of a laptop and a phone, we send a Wi-Fi signal between these two devices. Since we know that a Wi-Fi wave travels at the speed of light, we can easily calculate the distance if we know the time of flight between the devices. Wi-Fi is not as deterministic as a baseball, and there are multiple factors that impact our ability to accurately measure when a message is received. That's why we use a fine granularity counter for highly precise timing measurement, as well as algorithms to determine when exactly messages are received. In the case of wirelessly pairing screens without the need for setup, we need to understand both how far apart the screens are and if they are positioned to the left or to the right of the main device, say a PC. In these cases, knowing the range is not enough. We need to find a way of determining the directionality of a device. To determine directionality of a device, we again need true antennas, which we use to send messages to the device in question. Once the message is received, it sends back a message. Since we are listening on both antennas, we can measure the difference in time it took for the same message to reach the antenna. If the message arrives at the right-hand antenna earlier than the one on the left, then we know that the device we are pairing with is positioned to the right of the one we are pairing from. With the physical distance between the two antennas established, the time difference between when both antennas receive the signal, and the speed of light defined, we can calculate more precisely at what angle the other device is placed. Wireless sensing and proximity are fundamental technologies that unlock seamless and intelligent connectivity experiences. And this is just the beginning of what intelligent connectivity can empower. Now that we've covered some intelligent connectivity experiences, let's talk about the hardware that is empowering them from within our latest Intel Core Ultra processor, codenamed Lunar Lake. This new series of processors are the first to be built with Wi-Fi 7 and Bluetooth 5.4 integrated onto the SoC, specifically the platform controller tile. By moving the Mac onto the platform controller tile, we can save die space on the wireless discrete module, improving the thermals and allowing us to launch unique features like Wi-Fi sensing. If you want to learn more about Wi-Fi 7, be sure to check out my episode from Season 2 of Intel Architecture All Access. With the integration of Wi-Fi 7 onto our latest Intel Core Ultra family of processors, users can unlock a whole new world of connected experience with Intel Unison. Intel Unison was designed for secure, multi-device experiences across any device or OS. Additionally, Unison adds support for tablet control with our new Intel Core Ultra processor, codenamed Lunar Lake, meaning you can now tether your tablet and your PC to transfer files and photos between the two devices, extend your screen, or use your laptop mouse and keyboard to control the tablet. And with the addition of Swift Connect, you can now create temporary connections between a Unison-enabled PC and any other device, even if that device does not have Unison installed. We will also be adding a universal hotspot feature, which allows PCs to seamlessly tether and use a phone cellular connection to access the internet. For some experiences, we need very high and dedicated bandwidth to drive them. One such experience is Thunderbolt Share. This is a new feature that uses a Thunderbolt connection to allow users to connect PCs to one another directly via a single Thunderbolt cable. With Thunderbolt Share, users can enjoy up to 60 frames per second screen sharing, faster file transfers, and rapid file syncing. Ultimately, Thunderbolt Share is the fastest way to connect to PCs. For example, if you have a 100GB game on your gaming PC that you need to transfer to your laptop, you can do it in only 20 seconds with Thunderbolt Share. Intelligent connectivity is a constantly evolving area of engineering, and every day it's opening up a whole new realm of technical possibilities. New Intel client platforms already support some intelligent connectivity capabilities. We've just only begun to scratch the surface of what's possible. Thank you for joining me today in this episode of Intel Architecture All Access.